So today we're going to talk about heat transfer, going over your heat transfer notes. 3 ways in which heat or energy is transferred. First one is radiation. This one, the energy is transferred through the electromagnetic spectrum. This one, electromagnetic spectrum, is on your reference table, page 14. Radio waves, X-rays, gamma rays, infrared waves, visible light rays, all those are radiation. So when the sun is out, it's radiating. The lights inside, it's radiating. Your body is radiating heat off. Alright, so that's all types of radiation. Majority of the radiation that reaches the earth is in the form of visible lights. Radiation actually radiates out in all directions, so 360 degrees. Next one, we're going to look at convection. Convection transfers energy, or usually heat, through currents. We talked about this one when we did plate tectonics, because you had convection currents in the asthenosphere. That was what was causing the plates to move. The driving force of convection currents is density. More dense sinks, less dense gets pushed upwards. Alright? So this one, it says less dense gets pushed upwards by cooler, more dense material. This is going to be really important for you when we do meteorology and we look at cold fronts and warm fronts. As it leaves the heat source, it cools and becomes more dense. This one, if you're thinking about a heater, the heater that's in the classroom, it's sucking that cooler, more dense air up in, it heats it up. As it heats it up, it forces it outwards. That air is warmer. It's going to get pushed upwards by the cooler, more dense air. Alright? As it's left its heat source, it cools down, it becomes more dense, and it will sink. So you get that, and then it gets sucked back in the heater, heated back up. It's less dense, gets forced upwards by the cooler, more dense air. And then as it leaves the heat source again, it cools, and it's just a cycle. Remember, heat or warm air does not rise, it gets displaced by cooler, more dense air. That's a misconception, unfortunately, you guys come with. So I want to do a really quick drawing on this one. I have my beaker. I have water in my beaker. I have my Bunsen burner, which you guys will have next year with Mr. Miller. It's got my flame. If my flame is on this side, this is my heat source. So I am warming up directly above my heat source. So my convection current is going to look like this. If same concept, got my water, I'm just going to move my Bunsen burner to the middle. So here, I'm going to make actually 2 convection currents. I'm heating up, so this is my heat source, becomes less dense, it's going to curve and go out that way. This one's going to curve and go this way. So I get 2 going this way. So wherever my heat source is, that's where it's going to get warmer. That's going to cause that to get pushed upwards. Once it's left the heat source, it gets cooler and it falls back down. Alright, so that's going to be my convection. Next, conduction. Now conduction's got a D in it. D, direct contact, molecule to molecule. So it needs to be touching. So if I'm looking at it, the flame, whatever it touches, actually is going to heat. So molecule by molecule, I'm heating my water up if I have a kettle. So inside, we'll say inside my tea kettle, here's my flame. That's heating the bottom of the kettle up. The water molecules that are touching are going to get heated. All right, conduction. The water molecules then touching those water molecules are going to get heated. So what's happening is I'm making this warmer than the water up here. All right, that's unstable, and that's going to get me back to my convection current. All right? So they all intertie together. My flame is my radiation, molecule by molecule touching and heating and transferring that energy. It's conduction. Once it's unstable and the warm is down here and the cooler is above, cooler is more dense, it's going to force that less dense water upwards. So there are my three ways that heat is transferred. Radiation, conduction, and convection. All right, looking at temperature. This one you guys will talk about next year in chemistry. Temperature, you're measuring the average amount of kinetic energy. Remember, kinetic energy, half mass times the velocity squared. All right, temperature with that one, your energy is more when the temperature is higher, more kinetic energy. So your direction of heat flow is always from high energy to low energy, or high temperature to lower temperature. Couple terms really quick. Heat source, heat sink. Heat source is where the heat is coming from, or the higher temperature. Heat sink is where the heat goes to, or the lower temperature. A unit of heat is a joule. 1 joule is the amount of energy needed to raise 1 gram of liquid water 1 degree Celsius. So it's all based on water. Specific heat is the amount of, same thing as your joule, but it's not just water. It's the amount of heat energy needed to raise 1 gram of a substance, any substance, 1 degree Celsius. Liquid water has the highest specific heat. If you're looking at your reference table, page 1, you will notice that water has the highest specific heat. So therefore, it takes longer to heat up and cool down than any of the other substances. The higher the specific heat, more energy needed to raise and lower. So the whole idea, if I take you right now, today is one of those nice warm, humid days that we have in Syracuse. It's 86 today. If I drop you in Lake Ontario is not 86. All right, the lake in the summertime is a lot cooler than the air of the land because the water is taking longer to heat up. All right, if I looked at, say, October, end of October, the water is retaining heat, so Lake Ontario is going to be warmer. This whole concept is the reason why we have lake effect snow. Because a cooler, dry air coming from Canada goes over Lake Ontario. It's retained the heat in the wintertime. It's more warm, it's more humid, picks up all that moisture, and then when it goes across land, land has a lower specific heat. So it's cooler in the wintertime. So all that moisture gets displaced, or it drops out. So we get lake effect snow. So all has to tie back into specific heat of water. All right, the law of conservation of energy states that energy cannot be created nor destroyed. It just gets transferred from one form to another. The whole idea is when you're going from potential energy, when we did the river, you had potential energy when it was high at the head, and as soon as it started moving, it went to kinetic. Once it slowed down, that kinetic went back into potential. So it's just forming from one energy type to another energy type. Latent heat of fusion. On your reference table, page 1. 334 joules for every gram. I'm going from a solid to a liquid or a liquid to solid. So if I have 100 grams of ice, it's going to take 33,400 joules to change it to liquid water. So you just multiply the 334 joules by every gram that you have. Latent heat of vaporization, same concept as latent heat of fusion. This one I'm going from a liquid to gas or gas to liquid. Notice it takes a lot more energy to go from a liquid to a gas or a gas to a liquid. This one is 2,260 joules for every gram. Same concept. If I have that 100 grams of water and I want to evaporate it, it's going to take 226,000 joules to evaporate that 100 grams of water. Or in reverse, it's going to take 226,000 joules to actually condense the 100 grams of water. All right, as you go up the heating curve from a solid to a liquid to gas, heat energy gets absorbed. You're taking it in from the environment. As you go down the heating curve from a gas to a liquid to a solid, you release that heat energy back to the environment. So this one ties into apple orchards. Apple orchards around here, if we had warm spring and then all of a sudden the temperature really drops, what you'll notice is they actually spray water around. They're spraying water around so the water actually hits onto the little buds, and then as the water will evaporate, it's actually giving heat off. So it's just going to keep that bud warm enough that it won't get destroyed. So that way their crops don't get destroyed. All right, so it actually ties into something surrounding you. Absorption, I'm taking in. I'm gaining energy from the electromagnetic spectrum. Darker, more rough surfaces absorb more visible light. All right, the lighter colors, the smoother surface, they tend to reflect more. So they're not going to absorb, they're going to reflect. So when you absorb more, your temperature increases. When you reflect, your temperature increases less. All right, so if I'm looking at rough surfaces versus a smooth surface, that rough surface, that texture, has more surface area. So I have more surface area for absorption to actually occur. So if I'm looking at a forest versus if I'm looking at a beach, the forest, the darker colors, the rougher texture is actually going to absorb more than the beach. Beach tends to reflect more. All right, it's important to know, remember, we said most of our energy from the sun comes in as visible light that actually hits the Earth's surface. That's a shorter wavelength. You're back on your reference table, page 14, under the electromagnetic spectrum. That shorter energy gets absorbed by objects on the Earth, the land, the building, whatever. Then it gets re-radiated as infrared energy. That's a longer wavelength. That's what's getting radiated out to space. Now, if I have clouds at night, the clouds will bounce that radiation back, keeping us warmer at night. So the clouds act as blankets, keeping us warmer at night. If I don't have those clouds at night, heat's able to escape, my temperatures drop. The reverse is going to happen during the day. The clouds will cause some of that energy to get reflected back, so it keeps us cooler during the day, because our heat source during the day is the sun. The heat source during the night is whatever absorbed all that energy during the day. All right, so if I have clouds during the day, we're cooler. Clouds at night keep us warmer. Now, if I'm looking at a greenhouse, how a greenhouse actually works, and I'm talking where they actually grow plants. We have that energy coming in as mostly visible light. It gets through that glass. It gets absorbed by those plants. It gets re-radiated as infrared. Problem is that infrared light cannot escape the greenhouse, can't go through the glass, so it gets reflected back. So a greenhouse is always kept warm.